In this video, EMC's SuperSim flotation simulation program is used to simulate the performance of a copper-lead-zinc plant in southern Spain. Flotation kinetics of key streams are generated by conducting bench-scale rate tests on either a laboratory-prepared sample of mill feed or on grab samples of pulp taken from the plant. And this type of rate test is known as a hot float. A grab sample may or may not be representative, and if not, the flotation kinetics it generates will not be a true reflection of the stream's flotation characteristics. If this happens and you cannot repeat the test, what do you do? This video addresses this particular issue and also provides an example of how to use flotation kinetics to determine what is required to improve plant recovery. What you see here is the flow sheet for the copper-lead-zinc plant, where you have the copper circuit on your left, the zinc circuit on your right. Both have regrind mills. It looks very congested. That is because it's got a lot of options. These are valves where you can operate the circuit in open circuit or in closed circuit, and there's a lead upgrade here. You produce copper concentrate down here, lead concentrate here, and zinc here. On the third stage of cleaners, you can route that either directly to final concentrate or put that through a regrind mill, and that concentrate can go to the copper concentrate. The tailings can be rerouted, as you can see, into a further lead upgrading. There's a facility where, for instance, in these regrind mills, if I click on these, at the moment that has a regrind mill program in it, but that can be reset so that it becomes effectively a mixer. The control panel is where you have all the banks, and you have the number of cells, the volume of cells, and the air rate marked as a percent. 1% is the very minimum that you can put into a plant cell, and 100% is the very maximum. And down here you see there's a set of kinetics that you assign to each bank or each cell, and there's an air rate and water recovery rate relationship. Below you have the mass balance with all the analytes here, solids tons per hour, pulp volume, water recovery, percent solids, and all the various streams. What I've done to make it easier, I've made this into a summary table here. So you have the simulation and the plant data. You can see, as far as the copper circuit is concerned and the lead concentrate, that the simulation produces pretty much what the plant also does. In the zinc circuit, up until the rougher concentrate, this is also a good agreement between the simulation and the plant. However, you will find in the zinc final concentrate, you see the plant has a recovery of 71.88% at 48.3% zinc, and the simulation is much lower. Now the problem here is if we go to the kinetics and we go to that zinc cleaner bank, you can see here these are the zinc cleaners and it's assigned kinetic set 4. So if we go to the kinetics and go along to kinetic set 4, you can see that these are the kinetics of the gangue, copper, zinc, lead, etc. down to pyrite. And as you see on the left, you have a fast floating fraction, a fast rate, and a slow rate. And these kinetics are from test PZ5A. And you can see that the kinetics for the zinc are very low for a zinc cleaner. 34% of the zinc is fast floating fraction with a rate of 0.4. That's a fast rate, and a slow rate of 0.0188. The fast floating fraction of 0.34 means that 34% of zinc is fast floating, and this value is also a stage recovery across the zinc cleaners. This is low. Normally one can expect a stage recovery of 85 to 95%, so this value should properly be at least 0.85, and plant data shows that stage recovery is actually 88%. So let's see where that comes from. If I bring on board the actual test, this is PZ5A, which is the first cleaner feed in the zinc plant, and I scroll down and you see that it's got a head grade of 30%, and if I highlight the cumulative zinc cleaner concentrate, the zinc assay varies from 45 to about 41%. But you can see that its recovery, the stage recovery across the zinc cleaner in this rate test, is only 47% and a mass pull of 34%. So what do we do from here? So if we go back to the mass balance, unfortunately from the test what we have is that gave kinetics that are low and are not representative of the plant performance across these zinc cleaners. So what we can do is that we can go back to the kinetics knowing that the recovery in the plant is 71.8%, and we can change these kinetics as to what should they be for the simulation to reproduce what the plant does. Well, from experience I know that across a zinc cleaner the fast floating fraction, and I'm just changing it now, should be 0.85, or 85% of the zinc in the rougher concentrate is well liberated and is easily recoverable. The rate I know should be something like 1 or 1.25, and I'm going to leave the slow rate the same. So having changed that, let's go to the mass balance, and we'll keep our eyes on these columns here. Let's set the simulation in motion and let's see what happens. And you can see the figures change, not only in the simulated recovery and grade, but also in the mass pull, and also in the zinc first, second and third cleaner concentrates. So we see what that does, and you can see, having changed those kinetics, now that the simulation gives pretty much what the plant does. Now what also needs to be borne in mind is not only do the zinc kinetics change to actually what they should be, but also if you look at the mass pulls in the plant, the zinc rougher concentrate is about 16.6% mass and the final concentrate is 8% mass roughly. So that means the stage recovery from the zinc rougher concentrate mass to zinc final concentrate mass is about 50%. That means that the fast floating fraction of gangue should also be in the region of 0.5, because again that is a stage recovery. If we go back to the kinetics, and you see from this test that the fast floating fraction of gangue is 0.16, in other words 16% of the gangue is fast floating, and that is a stage recovery from rougher concentrate in this particular rate test to first cleaner concentrate. That needs to be changed to something like 0.56, and we can leave the fast floating rate of gangue the same and change the slow floating rate to 0.005. Again, let's go back to the simulation and see what that produces. You will notice that there's not much change to the zinc recovery because we're not changing the zinc kinetics. But you can see from the mass pull and from the grade that that has changed, and that is being reduced because I've increased the gangue kinetics. So now that has completed simulation, and you can see from the mass pull that the simulation is close to what the plant produces, so is the zinc recovery. Now you notice in terms of copper, which are in these columns, that there is not a very good agreement between simulation and copper. That is because I haven't changed the kinetics of the copper in this poor rate test. What this exercise has shown is that although that the original rate test gave poor results and therefore poor kinetics that were not representative of the plant, you can change the kinetics and define what they are so that the simulation represents the plant. Now this is a useful exercise because what you can do is that if you want to increase the recovery or grade in your plant, you can change the kinetics and determine what the kinetic values must be so that you get either 1 or 2% recovery extra in your plant. How do you go about defining what kinetics are required to achieve an increase in recovery and or concentrate grade? There are two ways to do this. Firstly, do tests and from the kinetics determine if flotation behavior has improved, or secondly, change the kinetics and use the simulation program to determine when the required improvement has been achieved. Then, put this new set of kinetics into ScrollCalc and reproduce the equivalent laboratory scale test. This set of recovery time and recovery grade curves becomes a target, and if they can be matched, then you know that the improved simulated plant recovery and grade can be achieved. Regrinding copper and zinc rougher concentrate in a copper-zinc flotation plant is an example of the first method. The graph shows rate tests performed on copper rougher concentrate as is and after regrinding, and the same for zinc rougher concentrate. In both cases there is an improvement in grade for the same recovery. Although not shown here, there were also improvements in zinc and iron rejection in the copper rougher concentrate, and iron rejection in the zinc rougher concentrate. The best way to see what is going on is to analyze the flotation kinetics. Here are the kinetics of copper rougher concentrate floated as is and after regrinding, and you have the same below for zinc rougher concentrate as is and after regrinding. For copper, regrinding reduces copper fast fraction and rate kinetics, and those of zinc and iron. Copper selectivity against gangue is improved slightly, but the big improvements are between copper and zinc and copper and iron. So regrinding is achieving what it should do, and that is to liberate chalcopyrite from sphalerite and pyrite. In the zinc regrind, the aim is to liberate sphalerite from pyrite, and not so much to improve selectivity between sphalerite and gangue. And the kinetics show that this is being done. Gangue kinetics decrease a little, but do not change zinc selectivity relative to floatable gangue. The real improvement is seen in zinc-iron selectivity, which indicates that sphalerite is being liberated from pyrite. If mineral selectivity is shown, it is clear that regrinding in the copper circuit improves the liberation between chalcopyrite and pyrite, and chalcopyrite and sphalerite, and regrinding in the zinc circuit improves the liberation between sphalerite and pyrite. The second way is more unusual, and this will be described in more detail. The next thing I'm going to bring into the screen is ScrollCalc. So what I have here is that I have a little program that compares two sets of tests. One, as you see here, is the zinc cleaner rate test as is, and this is the estimate which are the kinetics that I put into the simulation so that it reproduces what the plant performance is. Here it's zinc and the head grade is 28%. The kinetics go into the Kelsall equation, fast fraction here, fast rate here, and slow rate here. And the slow floating fraction is merely 1 minus the fast floating fraction. This gives recovery for values of time. Blue lines trace the original lab hot float rate tests conducted on a grab sample from the plant, and the yellow lines are derived from the kinetics that define actual plant performance across the zinc cleaners. What you saw before in the kinetics sets in SuperSim that were changed to reflect actual plant performance are laboratory kinetics. So the yellow lines you see here is the result of a laboratory scale rate test and is the laboratory equivalent of plant performance. In other words, if you achieved this result in the laboratory, generating these kinetics, then the zinc recovery in the plant would be 71.8% at 49% zinc grade, as we have seen in the plant mass balance. To confirm that these calculated results are representative, the recovery grade curve, which is almost vertical, ranging from about 42 to 48% zinc, corresponds to the actual test data highlighted here. And you can see that these values range from about 42 to 45 or 46% zinc. So now to continue this exercise, if I then take this away and we say to ourselves, right, we've got a plant recovery of 71.8%. What do I have to do in order to increase that zinc recovery by, let's say, 1 or 1.5%? Assume further test work involving, say, a finer regrind and a more selective reagent suite has optimized the zinc regrind step, and that zinc kinetics have been improved from a fast fraction of 0.85 to 0.88, a fast rate of 1.25 to 1.5, and a slow rate of 0.0188 to 0.025. Then go back to Kinetics set 4 and change the zinc kinetics to these new values. Remember that these are laboratory kinetics, which in the SuperSim program are multiplied by a series of laboratory to plant scale-up factors in order to simulate plant performance. Having done this, we go back to the plant mass balance and simulate these changes. The product of this is that recovery has increased by 2.3% from 72.9% to 75.2%. Note that mass pull and concentrate grade have not changed, because we didn't change the gang kinetics. We have three sets of laboratory scale kinetics which describe flotation performance across these zinc cleaners. The first are kinetics from the non-representative grab sample, which are not a true reflection of cleaner feed flotation characteristics. The second are kinetics which do represent the flotation behavior in the plant, which were derived by simulation. And the third set of kinetics describe a flotation performance we would like to achieve, and from simulation we know this gives an extra 2.3% zinc recovery. This set of kinetics becomes a test work target, and they describe a set of recovery time and recovery grade curves that are to be achieved by optimizing test conditions. To find out what these laboratory scale curves look like relative to the kinetics that are representative of current plant performance, we need to go back to the scroll calc method. Test float sample kinetics are at the top here and are shown by the blue lines. Kinetics representative of current flotation performance in the plant are down here and shown by yellow lines. What I'm going to do is to change the original hot float kinetics into the Optimise set so that we can compare them and get a visual idea of what the magnitude of improvement is that we need to achieve in the laboratory. So the zinc goes up to 0.88 as I put in the plant, roughly there. Fast forwarding rate to 1.5, and you can see what happens. This is quite a bit of fun actually when you start doing this. Let's bring that up to roughly 1.5, there we are. And the slow floating rate was 0.025. So we just use the little slider and put that up there. Obviously you see down here on the cumulative recovery concentrate grade, you can't have a zinc concentrate grade of about 350% because practically we've left the kinetics of the original rate test of the gang very low. So those have to go back up to what the plant is, which is roughly 0.6. I'm just going to quickly move it to roughly what these figures are, and 0.3. Let's move it a little bit back, and 0.0049, and obviously the plant, I'm just going to put it back to practical figures because either the rate or something would have also increased. So something like that. You will notice that some of the kinetic values are different to the ones quoted previously. Don't worry about this because I'm using rough values to illustrate the principles involved. To recap, the yellow lines describe a laboratory scale test representative of current zinc cleaner plant performance, giving a recovery of 72.8% at 48.5% zinc grade. The blue lines describe superior flotation performance, and by simulation we have seen that this increases zinc recovery by 2.3% to 75.2%. The task now is to determine what test conditions need to be changed, such as grind, reagents or pH, etc., in order to achieve these results. The improvement in zinc recovery time and recovery grade curves may seem small, but the effect on the plant is large.